Okay, so I hope everyone had a pleasant Easter break. We don't call this a break week from where I'm from. We call it a reading week, right? Because the idea is that you got a week off class to catch up. But I don't see anyone with tans. That's what usually happens in Canada as people sort of run off to Cuba, which is our version of Thailand or whatever. Okay, today we're going to learn about functors. So let's just recall what we've learned about higher order patterns, specifically map, right? So I introduced to you this map, which was an operation or a function that, given a function in a list, we could take that function and apply it to every element of that list. And the thing that was important here was that it was a structure preserving operation. That is to say, you can't map over a list and change that list's length, right? We can change the stuff inside from ones to trues, maybe, but the outer structure has to stay the same. Now, this is sort of what we want to now generalize today. We have a lot of data which can be thought of as being structure, and as soon as we have data with structure, we sort of want to be able to do something like a map, right? Am I able to go into that structure somehow and make internal types of changes? So functors are the generalization of maps. Or so it's the generalization of a function of a structure preserving type of operation. So this is going to be the name of the game today. At least in our first lecture, is sort of generalizing map. Can anyone think of any other type of structures and then therefore what type of structure preserving operations we can do over those? So I said something like list was a structure. So we could map over lists. So you give me something that goes from A to B. I think that's always going to be necessary to give me some type of function. We had some structure over A, and I say I want to make this now structure over B, right? So that was sort of map for lists. Can anyone name anything else with structure on it? Yeah. Tuples are a little bit okay. So yeah, yes, but you picked a trickier example. Because do we have one tuples in Haskell? I don't, can we? No, so that's the tricky part. Um, let's put a pin. Yours is correct, but I want that to be the final one that we do. So I'm gonna put that in here because we're gonna want to map some function um A over to B, and then you're gonna give me a tuple, right? So what's this tuple? Well, it has to have an A or B in it, right? Because like something over here, one of the positions in here is going to have to be an A. We don't know which. And then one of the positions over here has to be B, and we don't know which. Because the problem is we need to know what the structure. Okay, so here I could have written this like this. Structure over A, structure over B. That's like an equivalent way of writing that list. Maybe we'll just finish this. Okay, so remember that we're basically currying everything. Okay, so if I were to say, and let's go back to your X and Y. If this is X and Y, what's the structure? We have to think about this a little bit differently because I can really take this Y out and do something like this. Oh, is that, did I do the wrong one? Can I do, can I do one comma this and then give it a two? Yeah, I can. Okay. Um, So the structure here really is this, like make something the second member of this tuple. So this can be A, right? And then what's the new structure going to? Well, B, right? Because if I say, maybe I can say, okay, let's just call F this structure, right? The thing that says I am type X is in my first element of the tuple. You give me something else and I'll make you a proper tuple. So that I can replace like this. And then the structure becomes much more apparent in here, right? So in both cases, we have a tuple that's length 2. We're just changing the second position from type A to type B through some type of map. And this should already be, I think all of these things are built in. It's just that we don't have, it's not called map. So generically, what we have is called an F map, right? So F map is going to work over anything which is mappable. And the class of things that are mappable are called functors. Right, so this is where the title comes from today. So let's see if I can F map +1 over a tuple and see what happens. Like from this, what do you suppose which element is going to change here? Then yeah, the 2 should turn to a 3. Okay, good. And that's why the second one has changed and not the first one, right? Because this was the structure. Now, this was regrettable, right? Because this was supposed to be the last example in the sequence of structure preserving examples. So can anyone give me anything else with structure, more basic structure? Yes, sir, in the back. Pardon me? Okay. Yes, we can have a tree. Okay, so let's. I just happen to have a tree defined. Here's a tree. It's a special type of tree. It can't be empty, right? So I'm saying this is a tree which the smallest tree is a leaf, and otherwise you connect a tree with two subtrees. Okay, so what's the structure here? Okay, so if I want to map uh, this function over tree A, what are we going to get out on the other side? Tree B. Okay. And then we'll actually go ahead later on and develop this functor. But again, here was structure over something, and we're changing the interior of that structure, right? So we could take a tree and we could map greater than 0 over it, right? As long as the nothing changes about the structure of that tree, it's still going to be a tree with a left tree and a right tree and X many nodes, but the inside of the nodes has been changed. Can anyone give me a simple example of structure that you've been working? Yes, thank you. Okay, so can we map over maybe? Right. So if I have something that's like maybe A, would you expect that we should be able to do something like this? So let's see if this is already built into the system. Can I plus one map just one? Okay, but like here's the trick. It has error handling already sort of inside of it, which is going to become much more relevant when it comes to applicatives. Okay, so here's the one on the maybe type, which is the simplest, right? So here maybe like that decorator is the structure, and the interior is the thing being mapped on, right? So we went from maybe A to maybe B because you can go inside of the container and you can now mess with the inside of that container and jump back out. Here's fmap on tuples, right? And as we discussed, because the structure itself is something that turns that you give me a element and I make you the second member of a tuple for which the first element is already fixed. That's why the second element here gets mapped. And tree is another one, right? So if you have a tree and in its leaves are things of type A, then I want to be able to go and sort of like change all of those leaves according to like this type of function. So in each case, this is sort of the generalization of what we're doing with the map. Right, so think about what we're doing with the map. That is taking every list element and sending it through a function. And we're doing that now with anything that has a structure over it. So let's try to deduce the common pattern, right? So here's fmap. We go from maybe A to maybe B. Here's the one over trees. We go from tree A to tree B. Here's the one for tuples, which was a little bit trickier. But if we write it like this, then sort of the structure should be becoming apparent, right? The generalization of mapping is to be given a function that goes from A to B, and then something with structure over A, and then I'm going to give you something back with structure over B, where that structure is preserved. And that is to say, the list length doesn't change, the number of nodes doesn't change, the maybe isn't suddenly an either. Right? We're just changing what's inside of the container, but not the container itself. Okay. So recall a type is an instance of a class when that type provides a bunch of operations that the class defines, right? So to be included in like the number class, you needed like addition and negation and stuff like that. Functor is a class, right? That is to say, some types will be instances of this class, provided that they have a delineated functionality. So what do you think is required of functors to be what do you think is required of types to be considered functors? What single sort of operation do we need? Well, identity. Like that would be everything has identity. Yeah. Yeah. fmap, right? The single operation that we have to define for the data in order for that type to be a functor is to define the map operation. Okay. So let's do that. Okay, so let's see, is that what so not only do we have to, okay, we have to define a mapping operation, and that mapping operation has to satisfy these two rules. right? Because we can have stuff here which types properly, but totally destroys structure, right? If I wrote a map function which took every list to empty list, would that type properly? Yeah, is it structure preserving? Only for the empty list, right? So we can always define things with the appropriate type, but that doesn't necessarily mean we really have a structure preserving map operation. We have this, the map operation with that type, and that map operation has to satisfy these two rules. And the two rules are if you map the identity operator, you should not do anything, right? That's equivalent to the identity function, right? So if you think, what happens if you map the identity function over a list? Well, that list is the same. What happens if you map the identity function over the tree? The tree should stay the same. Think about my faulty functor, the one which I said all maps take every list to empty list. Does that satisfy rule one? No. Okay, so that's why we need some of these rules. The second rule is about distributing composition. It says if you map or fmap G composed with H, that's the same thing as doing fmap G compose that with fmap H, right? So these two rules are important. What tool do we have? Because we're going to write functors and then not be sure if they satisfy these rules or not. So what we're going to have to do is prove that the things that we write are actually satisfy these rules. But before we prove, is there any way that we can quickly develop confidence that the thing that we wrote, is correct? How can we quickly determine this? Yeah, quick check. So this is exactly why quick check was provisioned by Haskell. Because we're going to start learning about a bunch of, like, mostly these classes say you have to define a function of this type that satisfies these rules. And the rules are effectively properties. Right, so what you'd normally do is you'd write a functor in Haskell and then quick check these properties. And then it would say you've passed these quick checks. At which point do we conclude that our functor is mathematically correct? No, but we do have confidence that it's probably correct, because if it failed the quick tests, then it's certainly not a functor and we have to go back. Right, so writing a functor and then having it pass the quick test for those properties is a necessary condition for then going by your proofs, because at least your proofs aren't going to be pointless, right? That you're trying to prove something that is correct, hopefully. So here's an example of how the list functor was defined. So what you want to do is as you are defining any type of instance, we say I want an instance for functor for the list type where. Now here's the tricky thing. Haskell insists on using the type inference engine in functor instances or in any of these instances. So you may be tempted because it's good style to write the type signature or the type header, but Haskell will give you an error if that's the case. Nonetheless, we still put it there as a comment. Like not we the class, but we Haskell programmers. Okay, so we're going to put these type definitions into the instance declarations, but as comments, because they're still good to look at. Okay, so what did we need to define the functor for lists? Well, that's just the regular map. So anything mapping over empty list is empty list, and mapping f over this list is f of x, cons, map over the rest of the list, right? So there's your recursion, and fmap plus 1 does this, right? Takes 1, 2, 3 to 2, 3, 4, and fmap greater than 1 takes 1, 2, 3 to false, true, true, right? Just to show you that we can like jump domains if we want, right? So none of this is new, right? Because we've already covered the map. So let's try doing some new stuff. Okay, so we also have this infix notation for the fmap, which is something that I prefer over using fmap because it's consistent with what does dollar sign mean? It means apply, like pass the right of this dollar sign as input to the function f. So we're just sort of like leveling that dollar sign operator up to say, oh, I'm going to pass you like a bunch of values that are contained in structure, and you should evaluate over that, right? So it makes sense, right, to upgrade the dollar sign operator in this fashion because it's just sort of fancier function application. I'm not passing in single elements. I'm passing in a group of elements, and the groups can sort of change. So this is the functor rules as written in the infix notation. You can use infix or postfix or prefix. Doesn't really make a difference to me. This is one of the preferences that you're allowed to have. This is my preference is to use the infix notation. So I can say +1, map that to the list 1, 2, 3. You get 2, 3, 4. Greater than 1, map that to 1, 2, 3. You get false, true, true. What's this one? Oh, greater than 1, map that to. So if I tell you that maybe is a functor, what do you expect this to do or to return? Just false, right? The maybe is the I make the same mistake all the time. Just false, right? So this just doesn't work over lists, right? A list was a functor, but there are many other things that are functors, right? So if we go into here, you can ask for info on maybe. And one of the things that you're going to see is that it's a functor, right? And because it's a functor, oops, we are required to minimally have access to fmap, right? That's the minimum functionality that the type has to provide to be considered a functor. And I don't think oh, don't worry about this weird sort of left map. All right, okay, so how do we prove if a functor satisfies the functor rules? Because this is what I'm gonna have you're doing this on your homework, and and this is the long answer question on your exam. I can already tell you that, okay? Because it's submitted. So we have to do this by basically doing math, right? Because this is where the fact that Haskell can be manipulated like mathematical expressions is really going to start being powerful, right? Because we're in a rewrite system, so we can be free to rewrite Haskell expressions by the rules of Haskell. And if we can rewrite something on the left-hand side of here to be equal to the right-hand side, then we've proven that property. Okay, so remember these sort of rules. We have rule 1 about mapping the identity and rule 2 about the composition. Now, I have to give you another tool. Okay, so we're going to have to prove stuff on types, but some of those types are going to be infinite, or a lot of those types will be infinite. Like a list can be infinite, trees can be infinite. Probably if you're putting structure over something and that structure has substructure, then it's going to be infinite. So I'm going to have to upgrade your your induction to this type of structural induction. Have you students learned structural induction in this class? No, it's just a little bit different because our data doesn't have a strict total ordering. I think I'm saying that properly. That is to say, how can we order lists? Is there any way that we can order lists? Well, there's many ways we can order lists or any of the, huh? So like I can say lists of length 7 are bigger than lists of length 6, but then there's going to be an infinite amount of things that are of length 6. Turns out that's not really a problem, right? As long as we can recurse down so that everything that we're calling is smaller by some measurement, and as long as the bottom is the smallest, then we're okay. I just have to sort of like tweak induction a little bit to work in this setting. So we'll tweak it, and then I'll do a bunch of examples, and it should be okay. Okay. So suppose S is some recursively defined structure, which is basically all data that we've defined that's interesting. Like a tree is recursively defined data, right? Because you connect, a list is recursively defined data because you connect scalars with other lists. Tree is recursively defined data because you connect trees with subtrees. These things have substructure, like a sublist or a subtree. And there is some well-founded partial order on S, like the length of the nodes, the length of the list, right? Not a total order, right? I can sort of have like partially, like I know things of length 7 are bigger than list of length 6, right? That's a weaker type of ordering. So if you have some data which is recursively defined like this, then here's the new statement of induction. Structural induction implies that if your proposition is true for all minimum structures, and the tricky thing is there may be an infinite amount of minimum structure, and if P is true for any immediate substructure of X, if you can deduce from that fact that it's true at X, then PX is true as well. Right? So suppose you want to prove something true for a list. You assume that it's true for the tail, and then deduce that it's true currently at this level, right? And then you have a proof. So it's similar to induction with just a couple tweaks. So let's try this. Okay, so for your homework, you can do this. This is the easy one. Just prove that mapping identity is the identity. Let's focus on doing sort of the more tricky one. That is sort of the distribution of this composition operator. So for the list functor, so remember, we have two rules of the list functor. Anything maps to empty list is empty list, and basically the generic sort of map rule, like take the head off, put it through F, and then connect with the mapping of the rest of the list. Okay, so let's go ahead and try to prove this using our structural induction. When we're doing these proofs, the only thing that you're allowed to utilize are the Haskell code that is written on your paper and these the rules that I'm going to give you now, right? And I'm going to insist that every single line that you write is justified. And I'm not doing this because I'm trying to like irritate you through detail. This is going to save you from making mistakes, right? Because you should never write a deduction down or any type of rewrite. Like every time you rewrite something, that has to have come from a rewrite rule, right? So you better tell me what that rewrite rule was, or you've maybe done something wrong. Like justifying each one of your lines are going to make your proofs more likely to be correct. So here's like the set of facts that I want you to stick to. Okay, so our context is sort of proving something about the list functor. So we do get to like refer to the rule, like the actual written down rules of the list functor. Okay, so this is the starting point. This is the thing that we want to prove is a functor. We can take for granted these. So just call this sort of like a composition rules. I can't really prove them, but it's sort of like intuitively true, and we need to do this all the time. Right? This is just a statement about how do you evaluate compositions. I'm saying F composed with G given X is the same thing as F composed with G $ X, is the same thing as F $ G of X, is the same thing as F $ G $ of X, right? So I'm saying we can swap out any of these for any of the other things, right, as a rewrite rule. We're going to allow that. Okay, so here's sort of the thing that's kind of tricky if you've never seen it before. So suppose we have a function f, and it's the +1 operator. What happens when I apply f to 2? What do I get? Yeah, so I can say f applied to 2 gives 3. And that's a rewrite rule, right? So if you had written down on your tape f of 2, you could safely write down next 3 because we've applied f to 2. That's the easy one. Okay, but if you saw 3 on your tape, could you deduce, can 3 be deducible from f of 2? Are those two things equal? Well, suppose, yeah, f is the +1 operator, yeah. So here's the thing. We want to make two expressions look equal to one another. So I can say f of 2 rewrites to 3, but I can also say 3 rewrites to f of 2. I know that seems weird because normally we simplify, we apply, but I'm saying we can also do the opposite of that, and that's called unapplying. Now, you can't look at me puzzily, quizzically. Everything we do now is going to be dependent on you understanding that we can apply and unapply functions. So ask me questions now, or this is going to be a really weird lecture. Yeah. No, you just say unapply. And like, what's the problem here? There are many things that you can unapply to get 3. I could say 3 was the result of dividing 6 by 2. 3 was the result of like dividing 30 by 10, right? Well, you have to have a goal in mind. You wouldn't unapply to random things that aren't conducive to the thing that you're trying to prove. But this is tricky, right? You have to you're trying to say A is equal to B somehow. And the way to do this is to work downward by both until you get a common element. And then like flip one of them. So you go all the way down, right? So I'm going to show you a bunch of proofs today. And a lot of my unapplies are going to seem magical, but that's only because I've worked them out and then produced the proof that I'm going to show you, right? So don't think that you're going to have to produce the proofs in the same manner as me giving you the solution, right? The solution required some working. Okay, so let's now prove the rule 2 for this list functor. Okay, so here's the second rule here, second functor rule. I think on your, I can't remember on your exam. Again, your exam is to do something very similar to what I'm going to be showing you now. It's going to be a functor on some recursive data. So as with any induction, the first thing that we want to do is just define our proposition. Okay, but this is different. So like the proposition now doesn't take you from a natural number to truth. It takes you from like something from in the type to truth. Okay, so I'm saying let x's be an arbitrary list of type A. Right? The proposition at x's is equivalent to this statement being correct, which is the second functor rule. Okay, so what are we trying to do? I'm trying to assert the correctness of this P for every element out of the type list A. And there's an infinite amount of stuff. So the only recourse we have for proving an infinite amount of stuff is true is through induction. Okay, so the two components of structural induction are very similar to the usual induction, and that is to what is the minimum substructure of this type? Empty list. How many empty lists are there? One. Okay, so not too bad in this case. So we're going to proceed by structural induction. So the base case is let's demonstrate that the proposition holds at the minimum substructure. The minimum substructure is empty list. So now we just need to show that if I give this left-hand side empty list, that is equivalent to giving the right-hand side empty list. So let's go through. What happens when I map g.h to empty lists? We have like not many rules that we can apply here. So I'm saying we get empty lists because we apply g.h. And maybe I could say by 2. I just don't have a lot of horizontal space right now. Everyone's good with this? What do I do from here? This is the trickier part. Yeah, now we need to start unapplying stuff, right, to produce this and this. So I'm going to unapply gmap. So it's clear that I can say this goes to empty list. Do you believe me that this goes to empty list if I apply that? Okay, but these are equals. So the direction here is meaningless. All right, so I can say from empty list, we can get G maps over empty list by unapplying G map to empty list. Does that make sense? Okay, so what's the next step here? Unapply F to that to get this. And then I use the composition rules to say that. And it's proved. Any questions? Because this was the easy one. Yes.
Also say and also unapply H without looking at G and H.
Sorry, for
in between the third and fourth line.
This is the third, yeah. What? But we haven't touched H yet here, right? That's why I mentioned it in the next line. Do one thing at a time, right? Don't do many things at a time. Because for one, if you unapply 2 functions, I'd say, in what order are you unapplying, right? So you should only apply or unapply 1 function at a time, right? Yeah. Yeah. No, because what does it mean to unapply F and G? That we can unapply functions. F and G is that's an English combination of 2 proof steps. So I'm going to say no, hard rule, right? Unapply or apply single functions. Otherwise, it doesn't make any sense. Although, yeah, this was sort of the objective. But yeah, this is the minimum amount of steps required to do this one. Any more questions? Because we're going to do the induction step now. Okay. So we can therefore conclude that the proposition at the minimum structure is true, right? And the minimum structure here is empty list. Okay, I'm just going to rewrite our proposition up here. And now let's do the sort of more complicated step. So the induction hypothesis is going to be this. I'm going to say, okay, we're going to be considering this list, xcon x's, right? Lists of length n plus 1. Assume it is the case that PX is already verified. So that is to say, I'm going to try and work with lists of length n plus 1, assuming list of length n and less already satisfy this rule. Right? But we don't say it like that because I'm not always going to have a nice length measurement. So I'm saying consider lists that are a head connected with a tail and assume all tails already satisfy this property. And it is the case that if I have x cons x, is anything x is smaller than x cons x is trivially true. So that's the only thing that we require, is that we're sort of recursing on something smaller or inducing on something smaller. Okay, so we just now need to show that if I start from here, that I can sort of rewrite to the right-hand side of this equation. So first one's basically free, right? There's only one rule that we can actually apply in this case. So what is that rule? It's the functor definition, right? It's okay. So let's try to map over this. So what happens if we map this over that? Like considering this as a single function, it gets sent to x goes to that function, and then we connect with the recursion. So something like this, yeah? Right? X gets sent to g dot h, and then we recurse, right? We F map over the rest. Okay, now what? We use the induction hypothesis. That's the whole point of doing induction, right? Is to access some type of convenient truth that is going to help us determine the truth at this stage. So where can I imply the induction hypothesis? This one, yeah? Okay, so it's already the case that this is equal to this, because that's the induction hypothesis. So let's just go ahead and swap those out. Now what did I do here? Okay, so I'll just move some stuff around in composition rules. So remember, we're trying to get this. So what can we do here? What patterns do you see that we now need to start undoing stuff, unapplying things, like we did in the last example? Yes, sir. We can unapply F map of G. Let's see if we can discover that. In your head, okay, so we have G and we're giving something to it like a scalar, right? And then we're taking G and then we're mapping it over some list, aren't we? Doesn't that sound like the generic rule of map? So that is this, unapplying the G-map operator. Yeah, I know. All right, let's digest it a bit. Maybe we should have all had an extra block of Weet-Bix this morning. Is this okay with everyone? Like, if you don't believe me, like the thing about these unapplies, they're very easy to convince yourself that they're right. Just go the other direction. If you apply this G map to here, do you produce this? Yeah. So it's always easier to apply. Like, it's actually not easier to apply, but maybe at our level, that sort of conceptually makes more sense. That you give something to a function and it gives you an answer, not that you start with the answer and you produce like a function and its call. But we're allowed to do that in this setting because this is math. We're effectively sort of working with math. Okay, so we pulled the G map out. Is there anything else that we can unapply now? Unapply the H map, right? Because you can it's like this is literally the right-hand pattern of the F map operator, right? So from there we get H this, right? Unapplying H map with these composition rules, I can just drop dollar signs and put in dots, and thereby we've proved this. Okay, so we have proved that the functor for maps satisfies the functor rules. Well, I haven't proved it for the identity, but that would be trivial. Okay, but this is a mathematical proof that no, the Haskell code that we wrote, you can be guaranteed that it satisfies the properties that we're assuring that we've said that they've satisfied, which are going to be important because we're going to be building other class instances over functors. Like the next one we're going to do is an applicative, and the applicatives are going to have a class constraint that the thing first has to be a functor. All right, so we're going to be building more things over these, and the things that we're building over require properties, right? So we're going to require this property in particular for applicatives. Okay, so that's equation one, follows from the principle of structural induction. So on your homework, exactly like this, and I'll give you all of the sevenths. Okay? So again, you have to work in two directions. You have to start trying to work from this, like you have to do things by applying. Like you don't have to, but one strategy here is to try to apply from both ends until you get some common element. But what I don't want to see is for you to give me proofs that say, oh, A eventually reduces to C and B eventually reduces to C, so therefore A and B are equal. This is considered amateurish in mathematical proofs. What I want is one deduction. A equal B, like this. I want to go from one side of the equation to the other. So probably in here, there's like like I probably did this all the way down to here, and then did this all the way down to here, but then one of those things have to be flipped, right, to tie them together. This is the best way of presenting it. Just like A is equal to B, not A is equal to some C and B is equal to some C. That's an indirect type of way of doing it. Okay, so let's try to build a custom functor. We haven't done that yet. So here's a tree. And wouldn't it be nice if I could say like a map greater than 2 over this tree to get a tree now holding a collection of true false values? Is this a structure preserving operation that I've shown? Yeah, because like, look, the tree's vibe didn't change. Only the things inside changed, the bones, the internal state of this. Okay, so I have this tree. Let's just get rid of this. And let's just go ahead and define a functor. All right, so this tree is kind of weird, right? Because I didn't delineate an empty tree, which is totally fine. We don't have to have an empty tree. So let's just have an example. So here's a tree, and maybe it can be something like it's a tree which connects a leaf of 1, 2 with leaf of 3, right? Or like maybe this could have been a right tree, or I can say the right tree is tree leaf 2, 3, 4, leaf 5. Okay. And let's just make sure that we can load this. And do we have a tree? Whoops, what did I load? All right. All right, so let's see, tree. Okay, so we have a tree. So what I want to do now is define an instance of a functor for tree where, and what do we have to do? Well, I have to define an fmap operator. So this fmap operator has what type? Well, you give me a function a to b, and then you give me something tree A, and I give you back something tree B. Savvy? This is the structure preserving operation that we need to make. Okay. So the extremely important thing about Haskell is that we functions are effectively just transformations on data. And if this is the data, how many patterns are in our data? 2. So how many patterns of fmap do we need to comprehensively cover all of tree? Exactly. Okay, so what's the first one that we have to be worried about? Yeah, what does it mean to fmap this function over a leaf of A? Leaf of foo of A. Okay, what's the other pattern? Okay, so this is foo over a tree that has a left tree, an A, and a right tree. Tree. Okay, so let's just pump the brakes. Okay, so it has to look like this. I can't change the structure of the tree. I have to write that. Okay, so what goes in here? So this has to be a B now. Okay, foo of B. So you guys are too sharp for me today. Okay, what about this one? What goes in here? F map of food for tree left. And then the same thing over here. Okay, but I'm going to show you something cool. When you're defining the prefix operator, you're already allowed to utilize the infix operator. Okay, so I'm going to do this instead. So I'm emphasizing the pattern here. Right? Do you see the pattern? Like the question was, why did I include this dollar sign? I don't have to, but it's like I'm putting it there because do you see what's happening? Like I'm mapping some function over structure and I'm saying, yeah, like apply it, apply it. Oh, also apply this function, but the function has to be applied as a map, right? So so you can sort of see the higher order pattern here materializing in a kind of way, which was what the motivation behind this dollar sign operator being put in angled brackets. Okay, so I'm saying by now I should already be able to now say, okay, here's a tree. I should be able to say, let's map the greater than zero operator over this tree. All right. So now we have a functor on this tree. Can we prove that this is the case? Oh, yeah, let's do it. Okay, so we do not and cannot include type signatures here. This one, but do include them in your working. They're useful. Just make sure to have them as a comment. You're allowed to utilize this on the right-hand side only. You can't define the infix operator dollar sign, but you can utilize it. So I can't do this. This would have been illegal. Can't do that. But I can do this because recursion's weird. Okay. All right. Okay. So here's an application of our tree functor. But have we defined a functor? Okay. So if we're actually out working in the real world, the first thing that we should try to do is some quick checks. You could maybe go home and try writing some quick checks for these trees for practice if you want. So let's just skip it. So assuming we have done some quick checks and they didn't fail, we have confidence now that the functor that we've defined is a functor. So let's go ahead and now prove this. And this is going to be a little bit different. So try to commit this to memory, this functor. So specifically, we care about line 4 and line 5 here. What we're doing on the map defined on the minimum structure and the map defined on not the minimum structure. Okay, so here's the proposition. Okay, I'm saying we have a functor given like this and data given like this. And I'm saying let T be a arbitrary tree taken from this type. My proposition is given this tree that the following holds. And the thing that follows is the second functor rule. Okay, now this is a little bit trickier. So we're going to do structural induction now. What's the base case? Yeah, what's the minimum structure of this data? Leaf, yeah? How many leaves are there? Well, at least one leaf for every member of A. If this was leaf bool, you wouldn't have been right. But I get your vibe. It's a product type, right? So it's certainly not exactly one of them. It's many of them. So what does this mean for the base case? Do we have to do like another induction? Yeah, like we work in the base case with an arbitrary leaf. And we'll see that it won't sort of affect anything. But don't always be reaching for induction. Like I see this a lot on the exam where induction is being used in like really strange places where it's not appropriate. But okay, so we've identified the minimum structure. So we're saying, okay, let T equal leaf of X, like this being the minimum structure of tree A. So we have to do our base case. And all I'm going to do now is try to rewrite this so that I produce that. Okay, so basically the only thing I can do here is apply the map to this leaf. And what do I get? Right? G.H goes in. So by line 4, apply F map G.H. Now what should we try doing? Yeah, some unapplies, right? Okay, I use some composition rules first. So now I should be able to take the G out. Yeah? So there's the G coming out. And now I should be able to take this H out. There's the H coming out. And now I should be able to use composition rules to get the dot where I would like it to be. And therefore, I have concluded in the base case. Right? So the base case gets a little bit more tricky, but it's okay because this X was never relevant in any way. Right? The structure didn't change. That's the thing that we're trying to confirm here. Okay, so that was the easier part. Here now is how you do structural induction. And this is a better example than the list one, because for the list one, we maybe could have shoehorned that into regular induction by talking about list length. But this one's a little bit more tricky because there's like 2 ways that we can have substructure. So I'm just saying, look, just consider this tree. Consider a tree. And as our induction hypothesis, assume that the left and right, that the left tree and right tree substructure already satisfies the second functor rule. Or like another way of thinking about this is we're building trees from subtrees. So just make an assumption that all the subtrees satisfy the functor rules, and then show that any new tree that you build still satisfies the functor rules. And you can sort of see how that will prove it for every tree. Okay. So the only thing that we can do here is apply the F map. All right, so, oh, sorry, I take t and I swap it out for what I said it was equal to. Now the only thing I can do is actually apply this map. So the map goes in, we're mapping the left tree, we're evaluating x, and we're mapping the right tree. What should I do with this? Well, I'm now going to take this out, right? Because by the induction hypothesis, so let me restate that. Where's the induction hypothesis? In here. Yes. Here, so I'm mapping something along the left tree, and I'm mapping something along the right tree. So my induction hypothesis says I can already assume the rule works for the left and right trees. So I'm just going to take this and replace it with the statement of the induction, and the right-hand side gets replaced by the statement of the induction. That is to say, I'm already unwrapping this F map in composition in the way that we're trying to. But this is fine because we assume that this was okay on substructure. All right. The next thing that I can do is I sort of identify that, look, we have F map G to this. Here is a G that's really applying to that. And here's an F map G that's applying to that. I suppose I just sort of unrolled it a bit just to make it more clear. But can you see from this line that we can take out a G map? Okay, so that's the previous line. We're going to take out a G map, and we're going to be left with this. Is there anything else that we could take out? Yeah, now you can see that this actually is the result of mapping H to the tree. So now I can take out an H. Okay? And once we have those out, we just use the composition rules to get the dot that we want. Put T back by definition, and we're sorted. Okay, so we developed a tree. That tree was a little bit weird because there is like a potentially infinite number of minimum structures, but that didn't bother us. And we still managed to come up with a functor and prove that that functor exists. Are there any other functors that you could define for this tree? So here's the struggle with me giving you questions in this course. There are not many things that we can actually define. So I'm uncertain that there is any other functor that is actually definable in this setting that preserves structure. I can't see how else you would do it. But then you're mirroring the trees. No, the structure is mirrored now, right? So I agree with you that that types properly, but it doesn't, I don't think it would satisfy the second functor rule, right? Because things would be on the opposite end of the tree. So you can try to prove me wrong. Yeah.
So, like, for example, you know how you will prove trees differently.
Stop. You said the only thing you're thinking about is the recursion. Yep. We don't think through the recursion. That's an abstraction barrier that we shouldn't be concerned with, right? The recursion just does its thing. I don't want to think through the recursion. Yeah. 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 Yeah.
Depending on whether you access the left node or the right node.
I'm not sure I agree with you, right?
You know the diagram shows us.
Yes. Like we can walk through trees, like there's pre-order, post-order, in order, but I don't see how that's relevant for this. No, that's just ways of traversing trees. That's not even a map. That wouldn't even count as a map because we're taking a tree and turning it into a list. We've changed the structure entirely. Yeah. Yeah. Okay. So I don't think there's another functor that we'd actually be able to define on this tree. So for applicatives, for the list applicatives, there's like exactly two list applicatives that exist, and one of them is implemented by Haskell, and the other one we'll talk about. So yeah, that is to say, if I told you that maybe has a functor, by then you should already know what it does. Like there's not other things that it could do besides just change the thing in the just container. Nah, we'll let you out early. You've had too many breaks already. Yeah, I got to think of how to compress the. Remember, we're getting rid of file handling, but we can't get rid of I/O because it's literally the thing we've been building to this entire time. But I do have an industry speaker coming in the last week. They're like really excited to speak with you guys, so that would be a good one to come talk with. Okay, so applicatives. So to summarize what functors were, this was sort of like the notion that in Haskell we put containers over things all the time, right? We've seen this maybe container, we've seen this either container, we like tree itself was a container. So we wanted some way of like going into the structure and making changes rather than having to undertake all of this like uh, unpacking, repacking, right? So like a lot of your exorcism questions now are going to get a lot easier now that you can sort of map into structure, especially the maybe structure. So what I want to do next is introduce the applicative, which is another class instance, but this one is much harder to give a type of motivation for because it was provisioned because we need this for the monad, right? So like next lecture, when I introduce the monad, then I can give I can say, look, see, now do you see why we've defined the applicative like this? But this lecture, it's going to be hard for me to give any type of intuition about this because the intuition only comes by understanding the thing that requires it. Hooray, mutual recursion in education, okay? But like this may be something if for those of you going into research roles, this is what researchers like. They're like, you need to understand something for which there is no pathway to learning it. There's just a sequence of research papers which you have to understand concurrently at the same time because they're all interdependent. So just keep reading them until they all suddenly all make sense simultaneously. So maybe go into industry. Okay, applicatives. It is natural for us to now ask, okay, we've generalized maps from lists to maps over like structure themselves. There's like other things now that I would like to do with this map. So if I can map univariate functions over lists, and again, this won't be valid Haskell, but like I want to be able to do this. Give me two lists, and I want to put like a plus, and I want to map that plus over these two lists, right? Because effectively I was saying like, oh, mapping over a list was just basically giving me a bunch of function input, right? But like, what happens if my function is bivariate? Can we do that? What about something like this? If I want to have three lists as input, and I want to say, oh, map this trivariate function over these three lists, right? So I can get a 12, 15, 8. So what is this? Do we have access to something like this already? Zip width, right? Zip is the function that takes two lists and give you tuples. Zip width is the extra one, which you have a function. I think this was one of your magic questions. I can't remember. Depends on the year. No, okay, maybe last year then. But one way that we can conceptualize applicatives is by generalizing zip width. That's the best I can do at the moment, right? So this is kind of like generalizing the zip width operator with error handling. Okay, so like those two things at the same time. Okay, because effectively, in terms of like having a practical objective for what we're doing today, the applicative is going to allow us to do this. Don't worry about too much about what I'm saying. I know you don't anyways, but especially now. Pure plus. That's what we want to be able to do. Like be able to say, I have stuff with structure in it, but I also want to like apply functions in and through that structure. It's kind of like zip width on jest, if you will. Now, the relevant thing here is that this will happen. Right? So this is error handling. Right? Okay, so maybe we'll do it like this. Remember this data type? If I tell you that either is an applicative, do we expect this to work? Yeah, why wouldn't we expect it to work? It's just a container. Okay, but I also told you that this provides error handling. So what was the either data type provision for? Yeah, basically for giving us more robust error handling. So if I were to say this, what would you expect? That's the error. Okay, so what we're going to do here is a twofold, right? Trying to operate over data, which are like wrappers over stuff. And I want to say ignore the wrappers and do this inside. But as well, sometimes these wrappers are used because of error handling. So I also want this error handling to be automated somehow by this type. All right. Okay, so again, just think we're generalizing zip with so that it also handles the error handling. Okay, so what's one way that we could do this? Well, I can just say we have a map operator. This is defined in Haskell. Why don't I define fmap2 to be this and like fmap3 to be this? Should I do this? Like, no, I shouldn't do this, right? Well, but it would work, right? If I had this, this would work. So, but the question is, why is this approach insufficient? Yeah, we're hard coding it. That's bad. Haskell's already huge. Yeah. There's an infinite number of these, so you better start writing now so we can finish before heat death of universe. It's not going to work. Conceptually, maybe it would work, but practically speaking, this is not something that we can sort of put into Haskell. So we're going to now introduce another class called the applicative class, and it has these two functions that are required of us to define in order to be included. And as I said, this is the first time we've seen a class, or well, I think this is the first time we've seen a class defined with a constraint. Remember we were studying these arrows? All right, so this means to say you can be an applicative of f provided that f is a functor. So given that f is a functor, what do we assume we have access to? A mapping operation, right? Okay, so the idea here is these things get defined with map. And if you're not using map to define them, you've probably done something wrong, right? Because that's why we need that constraint. Okay, so the first rule here called pure is just a way of saying, get me into your structure. Like I'm saying we're like going to go into structure. So you just tell me how I wrap something in structure. That's what this rule is, right? So if you're a list, I would give you one, you give me singleton one back. If you were a maybe type, I'd give you one, you give me just one back. Right? Put structure over A. That's the rule number one. This, which is sometimes called the spaceship operator because it kind of looks like a TIE fighter. I'm not actually sure how to call they just call it the applicative. So I'll probably refer to it as the applicative, but others do refer to it as spaceship operator. I don't mind that either. This is like, you can sort of see what we're trying to do here. Right? So this is a little bit different than map because in map, we just sort of ignored that F. And I'm saying I have a function that takes you from A to B. You have structure over A, get structure over B. This is a little bit different. I'm saying, oh, everything's trapped in structure. I have a function in structure, and I have A in structure. And I want to somehow apply that function trapped in structure to that data that's trapped in structure. And that's what this is going to do. Okay? We can just tell that from the typing. Okay. Not only do we have to define functions that type like this, they also have to satisfy a series of laws. And the reason I'm telling you that you are have to prove a functor on your exam is basically me telling you you're not going to do an applicative on your exam because the applicatives are a little bit tougher, and by a little bit. So maybe on your homework, but certainly not on the supplementary exam. Perhaps on the supplementary exam. Okay, so the first law is this: if you pure ID applied to X gives you X. So this is sort of a statement about you should be able to applicative identity, and that doesn't change anything. This effectively is saying your structure better not change. Right? If I do nothing, you should look exactly the same as I left you. Pure of G and X goes into that is the same thing as pure G applied pure X. Can't give you much motivation. X applied to pure Y is the same thing as pure. This is kind of funny. I'm saying that the input to the function is fixed, but you're giving me the function, right? So it's like I have Y, you give me a function, and I'll evaluate that at Y. This is just a statement about the order at which you have to. This is sort of like a commutativity type of statement, right? And this is sort of like an associativity type of statement, right? We're close to being associative. We're close to being commutative. You just have to add a bunch of these sort of changes in there. But don't worry too much about developing any type of intuition about this, because it was like the reason this exists is because the monad needs to do a bunch of stuff, which requires a bunch of functions that are typed like this, and requires that those functions satisfies these rules. Right. So again, like I don't try to understand too much of this. We're just going to sort of try to play with some of these definitions. So here's a corollary that allows you to switch between the applicative forms. So let's go back to here. So it was the case that so now we know that this pure was actually, okay, let's go up to here. The one with the jest. Okay, so now we know that this pure is actually just putting the structure over. So we can do that. But there's another way that we can do this where we drop that structure and we just do a map instead, and it's the same thing. And then these are the two forms that most Haskell programmers use. This is another point of preference if you want to do the first thing or if you want to do the second thing. But they're like type equivalent. So let's go ahead and try to prove some of these now. Okay, so the maybe applicative. So I showed you that the applicative exists. That's what this is. So let's check out what it's defined by, or maybe actually maybe more fun if we try and program it. Okay. So let's go up here. So I won't be able to run it, but let's remember. So data, maybe A is what? We have nothing or just of A, something like this. So if I want an instance, this has to be a functor of F gives me a applicative. Oh, I don't have to do this. Instance of maybe A, because it is already a functor, where, and I now need to define what? A pure function, which takes A to maybe A. And I also have to define this spaceship structure, which is going to take structure over a function and then structure over A and gives me back something with structure over B. Okay. Let's start. So there's two patterns here. So everything has to account for these patterns. Although this one we start with A, so that's easy. So what should pure A be equal to? Just A. Okay, that's easy. Now I have this, and we have to worry about two patterns. What it does with nothing, and what it does on... am I doing this right? Oh, sorry. Just nothing. Oh, no, nothing. Nothing is maybe that function type. Here would be just of foo, I guess, or just of F goes to A to B. Okay, so those are the two patterns. Is this correct? I have nothing. I have just, and I need maybe A. And this is maybe A. Okay, so what should I give here? Yeah, I think it's appropriate because like this is the error handling. As soon as nothing has been introduced, we should just end the show, okay? What should I do here? So I have a function that goes from A to B, and I have something with structure over A. How can I get something with structure over B? Use the functor, right? So here I can say this is FAB maps to maybe A. Everyone agree that this will at least type properly? Any questions? I hear some silence. Like, what else would we be able to put here if not this? Like, we'd effectively just re-implement a map in this case. Right, so when working with applicatives, like you want to use map, like that's sort of going to be necessary in this case. If you haven't used map, you've probably done something wrong when defining an applicative. So I'm not going to be able to run this because Haskell won't let me overwrite it. Well, I can just show you here. That's exactly what we discovered. And that's already going to start letting us do, okay, well, you tell me if this is going to evaluate or not. And what will it evaluate to? Right? Because this is just two. But do you see now how the other form falls out of here? Like this was just a map. This was just a map of +1. This is what that was what the definition of two is. So this is why we can always replace the front one here with a dollar sign. More exam hints. Every exam, I usually give you some statement with like this spaceship operator in it and maps, and I say bracket it in such a way where it evaluates. So you need to know how to sort of evaluate these things. So give that some practice. Um, what about this one? This will be just 3. What about this one? Same thing. And then this one is just showing you that the map is also sufficient, right? So just a bunch of different, just showing you that the maybe applicative that we've defined gives us this type of behavior. Okay, is this going to work now? Yeah, we're gonna get just 6. I can go into lists if I want, and we can also like move through domains. I can say take X, Y, Z, and ask if the product of X and Y is greater than Z. We get something like just false. Okay. Applicatively, okay, so now we're going to talk about all the laws, and I'm going to try to give you some intuition about why the laws have been defined as such. And then we'll try doing some proofs, and then maybe trying to define an extra list applicative. So applicative law 1, applicatively mapping the identity function has no effect, right? So effectively, this is checking that the structure hasn't changed. So here's a proof for maybe. Now, do we need induction here? Does maybe have like infinite substructure? Does maybe recurse on itself? No. So like we don't need recursion. We don't need induction here. This data type isn't recursive. It's a product type. There's an infinite amount of stuff in it, but it's not a recursive data type. Okay, so the reason I'm showing you this is just to demonstrate that you're not always going to be using induction or structural induction. Sometimes you just need to just do a rewrite. Okay, so how can I prove that this is the case for maybe? I'm going to say, okay, here's the proof for maybe. Pure ID cons X is equal to, right, and the assumption here is that like X is of type maybe A. Right, so X is going to be something like just or nothing. But at this point, we don't actually care what X is because we're just applying the rules, okay? So if I start here, to apply pure to the identity function is just to put the just decorator over it. So that one's easy. Where can I move from here? Well, we only have like one rule to apply in this case, right? And that is to say, okay, identity gets applied to X. And if I map identity to X, what happens? Y. This is identity of X according to the first functor rule, which is X. So I didn't even need to do a case analysis here. There was no requirement for me to say, okay, assume X is just, and I'm going to do another one for assuming X is nothing. This was all handled, right? And I've if you don't believe me, here's all the justifications. Okay. Because if it was nothing, all of these things would still be true. Yeah. So it doesn't matter, right? Maybe it's short circuit. I think maybe immediately you get nothing. You get pure ID applied to nothing is nothing is nothing is ID nothing is nothing. But if nothing will, if X being nothing doesn't violate any of the truth here. Okay. Pure distributes over normal function application. That is pure preserves function application. So that's sort of the interpretation of this, right? So pure of G $X is pure G spaceship pure X. So let's prove this for maybe. Okay, so pure G applied X. I'm just going to replace pure with just. And then I can replace that with the map operation because that's what it's defined, which replaces that with, what did I do here? So I applied pure to get that. And then I unapplied G, right? I unmapped it to get it out. and then I replaced it with the map with the pure version, right? Because we always have that I can either use pure G spaceship or just G map, right? There was a corollary I gave on like the slide a couple before, right? So we just unapplied this applicative operator, and then we can reverse this just back to pure, and that's exactly what we need. The result follows. Okay. So here's, so I don't really understand how to give higher order reasoning for this, but this is what Hutton says in his book, which was loosely the secondary text that I gave for this course. He says, when an effectful function is applied to a pure argument, the order in which we evaluate the two components doesn't matter. Like, again, eventually we're trying to build up a monad, which is going to be a piece of like a language feature that temporarily lets us sequence stuff. Right, so that's why the term sequencing is now showing up. So he's saying the order in which we evaluate in these sequences won't end up mattering, and this is going to be an important feature for when we define stuff for monads. So again, we'll come back to this when it becomes more relevant, but we can still prove stuff. Okay, so note that this funny thing here is holding the input to a function fixed, and you give me the function input. It's equivalent to $y, if you prefer that notation. So equivalently, this rule can be stated like this if we want. Okay, so proof for maybe, and now it's going to be sort of necessary to branch. So I'm going to say, okay, for now, let's assume that x is equal to just a. And we note this. So I want to show that when we apply this, that we'll end up here. And that's going to be a little bit tricky. So let's go. Okay, so pure apply y applied to just a is going to be equal to this by the definition of the spaceship operator. Did I hallucinate this? Yeah, this is just the corollary. Because we're allowed to replace pure that with a $sign. So I think maybe that justification is wrong. That should say by corollary. So we're still fine. I then should be able to map that in to get this. And then how do I handle that? Now that's this, right? Because a is the function, which we're holding fixed input y for. So we get that. And now what do you think we can do from here? We're just trying to like change the order of stuff, right? So we've managed to permute the position of a and y. So now I should be able to take a out, right? By like anti-mapping it, if you will, or unapplying the map. And then unapplying the corollary to get that. And then replacing just a back with x. And then unapplying the pure. Okay, so indeed, we've certified it for x being just of a as desired. But I'm just going to go ahead and do it for nothing now. I'm not sure that we have to, I'd have to, no, I think because we've done this, I've assumed that that position was a jest, that we sort of have to now do a case analysis. Right? Because I'm saying, oh, it's just. Well, if it was nothing, then the whole thing is borked. So let's do it again now for nothing. So what happens if I apply this to nothing? Nothing. Okay, so I'll do the corollary, get nothing. What happens if we map to nothing? It's nothing. So we can unapply anything from nothing, right? So, okay, I'll unapply the thing that I need, right? Sort of like multiplying anything by 0, right? But this was good. That's why I like sort of playing with the nothings is uninteresting, because you can materialize basically anything out of a nothing. Like the base case always comes from that nothing, but you do have to be careful in some of these case analyses. Oh, okay. We have this sort of loose associativity law that if you right bracket along the applicative, if you remove those right brackets, then you have to throw in this composition operator on the left. So it's like kind of associative. It's associative with this extra sort of nuance added into it. Right. So the problem is here, there's 3 things. And each of those things can be just or nothing. So like how many cases technically now is this proof going to induce? 8. Do I want to write 8 proofs? No. Okay, so I'm going to give you some leverage here, but don't abuse it. Like if you're really like put into a position where you're going to give like 8 proofs and 7 of them are basically identical, you can tell me that. You can say, look, this proof I'm going to give is the next one is going to be virtually identical to the one I just gave. So I'm not going to do it. Right? And so I'm going to say I did one case, case 2, and then maybe case 3 through case 8 are very similar to this. So just repeat. I'll leave this as an exercise to the user. I'll allow you to say that, right? But just be careful when you're saying that the cases are identical to the one that you just gave, that it is effectively identical, that you're just issuing some type of name swap, right? Because the thing is here, if I put a nothing into here, that nothing's going to propagate immediately. Everything will become nothing. If I put a nothing into here, that nothing's going to immediately propagate. Everything will be nothing. The same is true for Z. So I don't therefore care about, oh, what about if X is nothing, and Y is nothing, and Z is nothing? It's, I don't care. As soon as one of them is nothing, it all becomes nothing. So let's take all of the cases where at least one of them are nothing, and I'll do one of them, and then just say, if you have another nothing, it's going to look effectively like this. Really, the true case I care about is when none of them are nothing, right? So although there are 8 cases which we could delineate, there are really only 2 categories of cases. The one where everything is not, nothing, and the case where at least one of them are nothing. So it's not really 8 cases, it's 2 cases. So let's start with the one case where we're assuming nothing is nothing. So that's the initial statement of the rule, and we need to now deduce from this the right-hand side of the rule. Okay, so I've just replaced pure with just, and I can't give the justifications now because I don't have wide enough slides. So pure just gets replaced with just because we're sure of our type. I'm just going to sort of put brackets around here because that's the natural sort of operational precedence of these operators. I am then going to, what has happened here? Yes, did I miss am I losing a bracket or am I just getting really tired? Oh no, there it is. Yeah, I need the rule. Where's the rule? Yes, so I want to take this composition operator, yeah, and map it to A. That's what's happening, right? So we're mapping composition operator to A, which seems a little bit weird, but it's totally fine. So this is waiting for like another function in order to be fully composed. But we just applied the spaceship operator. Next, what are we going to do? We're now going to, yes, apply another one. So that brings this just inside to here. And then we're going to apply again, which gets this C over to there, right? These are all just according to the rules of these spaceship operators. And now I can start, I guess, unmapping all of these things because the real objective here was to sort of change the order of stuff. So I'm just going to use the corollary to put in dollar signs and try to start materializing the dots I need now. So I can take out an A, right? So we can either sort of unmap or unapplicative with the just there. I can do that again for the right-hand side here, right? Because this can be replaced with this. And then we replace all of these just back with what we presume they were. And then we have this as desired. Okay. So you could do the other one with a nothing, but it's okay. That's the other category. Okay. So this is the whole reason why this was provisioned, because now I can have like an atom function, which takes 3 inputs and returns their sum. And I can say, okay, pure atom, just 1, just 2, just 3, just 6. Pure atom, just 1, just 2, and nothing is nothing. Pure atom on just 1 and nothing and just 3 is nothing. Pure atom on nothing, just 2, just 3 is nothing. So we've like sort of accomplished this objective of introducing a zip with operator that additionally handles error handling. Okay, so exorcism questions should now become a lot easier, right? Because you don't have to unwrap and wrap things in the maybe structure anymore, or unwrap and wrap things in the either structure. I think, in fact, some of the questions from this week is effectively go look through your exorcism questions and try to simplify them now that you have functors and applicatives. Yes, miss? Yeah, of course. Yeah. I think you may have to. I'm thinking properly. Yeah, yeah. Yeah, check in your A2. You may have defined maps, right? Which you just have access to. Yeah. A few years ago, people were using the applicative on A1. That was remarkable, right? I'll tell you why. Okay. So this is the list applicative. Right. So now the question is, well, actually, this would be interesting. Let's talk about this. Let's see if we can define a applicative. Okay. So this is the list for lists. Let's give this some thought. So what was a list? A list over A was something like it's the empty list, or it's A connected to something that's list of A. Right, that was the type. Or maybe if you prefer, I can do something like this. Something like that. Okay. So the list of A is either empty list or it's connecting something A to list of A. So in order to define an instance of an applicative for list, we need a pure function and we need, what was the other one? Yeah, spaceship operator. Terminology is kind of growing on me, which means we have a list of functions and a list of A, and we need to return a list of B. Okay, so how should I define these things? What does pure A mean in this instance? How can I return something that is list A when given A? List A, that one's free. Okay, what about this one? So I'm going to give you a list of F8, like you get a list of functions, and then you get a list of A's, and you need to give me a list of B's. Well, one way to do this would just be zip with apply FAB's A's, right? Would you like, would that kind of work, right? This is sort of like if you have +1, +2, +3 on 0, 1, 0, and 1, you end up getting 0 plus 1, 1 plus 2, kind of like that. And that's a valid applicative, although this now is wrong. You'll find that if you work it out, we're going to have to change that to something. Indeed, I left this as an exercise at the end of the lecture. Right, so this would type, and it does actually lead to a valid list applicative, but that's not the one that Haskell is using. So can you give me anything else that will type here? All it has to do is type. How do I get, yeah, something of B? Mm-hmm. I think that's a great idea. Pop out a function from the list of functions, and also pop out an A from the list of A's. Makes sense? Okay, so if we had this example again, +1, +2, +3 along 0 and 1, this is going to be equal to the list comprehension, what? Yeah, like 0 plus 1, 0 plus 2, 0 plus 3, 1 plus 1, 1 plus 2, 1 plus 3, 0 plus 3, 1 plus 3. Did I do this wrong? 0, 1, 0, 2, 0, 3. Yeah. 1, 1, 1, 2, 1, 3. And that's it. Yeah, sorry. Yep. Unlike zip, it doesn't care that but the weird thing is the response is going to be a lot larger than the thing that you put in. This is the Cartesian product. This is what I'm trying to get at. Okay. So indeed, this is how Haskell has defined applicatives for lists. So if we look at the list type, how do I look at the list type? Like this? Yes. We have an applicative defined for it. And let's just see what it does. Okay. So what happens if I'm going to sort of map tuple to this? And the reason, you need to know how the Haskell list applicative works for your exam and for Haskell programming, but you care more about the first part. Okay. what do you suppose this is going to return? Right? All right, this is the Cartesian product. If I can even expand it a little bit more, we'll put a 6 here. Whoops. Oh, I need double constructor. Okay, so you got to remember that in its natural state, the list applicative is going to build for you the Cartesian product of the stuff that you're giving it. Right? But that it just becomes a little bit more unclear when I do stuff like this. Right? Because then the first position is what? Yeah, 1 times 4, and then 1 times 5, 1 times 2 times 4, 2, right? It's like this seems very strange unless we sort of go back to here and be like, Jesus, there was like exactly 2 things which were definable. Right? So so what I want you to do for homework, or maybe we can try to do it now, maybe, is try to do the other one. Right? There's another list applicative that would work that if we did it with zip with instead, but it changes it. Okay, so let's go back here. So the list applicative is operating by Cartesian product, which is very important. So let's test our sort of knowledge now. Is this going to work? None of these questions. Like, is this a valid Haskell expression? Yeah, it's fine because you can just replace that spaceship in pure with a map, right? So you can just do that, and then if the map didn't make any sense, then we can say no, this is not a great expression. What about this one? I hear some head shakes. I hear some of these. Well, for those who will think it returns something, what will it return? List of 3. That's fine, right? Because this is going to be like it's sort of evaluating from the left. That's the tricky part here. You're going to get like the Cartesian product of all of those pure pluses along with ones. So that's going to leave you a bunch, like a list with a bunch of like things that are going to evaluate +1 across. Okay, how about this one? So remember, Cartesian product does what? Sorry, applicative on list gives Cartesian product. Right, so 1, 3, 1, 4, 2, 3, 2, 4. Product of all of those things will give you that. Cool. Yeah, sort of like this one just makes it much more evident that it's giving the Cartesian product. And this is what my students gave me in A1 like a few years ago. Yeah, and I sort of called them in. I said, this is so amazing that you understand what this does. Please utilize it to do something else now, or we're going to have to talk. It was so bad that I said to the class, I'm going to reopen Gradescope and you can upload a blank file if you want. And I'm going to do this. We're going to forget that you all cheated in wide scale fashion because it was my fault. Everyone just sort of looked up, like, how do you do Cartesian products in Haskell? And what do you think came up? That, right? So this is why now things are banned. That's why if you look at A1, there's a bunch of things that we say you're not allowed to use, basically to thwart anyone who's asking the internet, how do I do this? Because bare minimum, you're going to have to at least understand how to remove, like swap out like an applicative with, well, yeah, you'd have to write the applicative in. I think, yeah, you'd probably be screwed in that case. Anyways, Cartesian product for this list. So just notice again, this is important, right? That you can always replace the front part here, this pure G and the spaceship operator with a G without its pure and this $sign. You're going to see both, right? There's not a standard here. This is sort of up to preference. My preference is this one for some odd reason. I can't really say why. Less is more in terms of writing programming. Right. So I think we did all of these. I'm not sure why I'm doing it again. Okay, so here's an exercise, and maybe we can talk about it for the next 10 minutes. I want to define another list operator or list applicative, but the problem is, since there's a list applicative already defined in Haskell, I can't define another one. So what we're going to do at first is just define a new type which is just a decorator over lists. So we can define another list operator. So let's do that. Okay. And get rid of all of this. Okay, so we have a new list. It's called the zip list. I'll show you how it works. Whoops. Why is it complaining? Did I write this wrong? That's just the decorator. So yeah, that should be fine. Is it not deriving? Yes, geez. So that's okay. Sorry, that should be a capital in there. Right. So I should be able to do something like, okay, give me a zip list, zip x's, which is just like z over 1, 2, 3. Okay. So we just now have to sort of deal with this ugly decorator, but it should do. Okay. So let's maybe try to do, let's do the functor first. Okay. So we can say instance for a functor for zip list where, and I need something which is the fmap operator, which is going to take a to b and zip of a to zip of b. So fmap of f to a to b to, now this is the empty list, like this. What should I put on the right-hand side? Yeah, zip of empty list. And let's say fmap of fab to z. This is the ugliness of these decorators. Xcon x's is what? Yeah, I take FAB and I send, oh, I'll change this to an A. A's. Take FAB, give it A, I get a B back. Then I connect it with taking FAB and mapping that to what remains. Yeah, let's see if that works. Maybe that needed some decoration. Do I need two? I should have never tried to do this live. No, I think there needs to be here. No, but it should be utilizing the cons of A. I shouldn't have tried this. Okay, someone help. Something is wrong. Okay, let's see if this will even work. Okay, that's fine. Will this type? Okay, we're still good. Okay, so I need to return a zip list. So that Z has to be there. And the thing that I want a zip list to be is, yeah, connecting. Oh, right. This. Yeah, I guess we can do this. I can say FAB over A and then take FAB and map to that over A's because the other thing has a functor. Okay. So I should be able to map over that zip list now. So fmap over the, oh, I'll do this one. Map over the zip list of 1, 2, 3. Okay, cool. Okay, so let's do the applicative now. That's working with these decorators is always a pain. Instance, applicative. I'll try it in the next few minutes. Applicative for zip list. Where maybe I'll set you up with the regular one, and then you can try expanding it to the zip list one. Okay, so what do we need here? We need a pure function which takes A to zip list of A. So that's going to be pure of A is Z of A. And we also need the starship operator to take something with structure over Z, A to B to Z over A to Z over B. Okay, so how did we define this normally? We said, okay, so you have something which is a list of functions, FABs. And then we have something which is a list over, which is list of A's. And I want to return something Z, which is that list of B. So the normal list applicative would be what? You take an F, you take an A, and F is drawn from FABs, and F is drawn from, A is drawn from A's. Okay, so we should now have I should now be able to do this over our new list applicative. So zip list of 1, 2, and zip list of 3, 4. Perfect. Okay, so I've set this up. So now the zip list sort of now behaves with the same applicative that the Haskell operates on. Now, I want to change this one to the other one that types. Now, I'll remind you, there is this zip with function that does this. So let's use zip with instead. So we just have to be careful because all of this, oh no, because I have that. Okay, so I want to zip with what am I zipping with? Apply, I believe. FABs and A's, and then we have to put the decorator on it. Okay, but I don't think this isn't gonna work now. Like this is fine, but now this is kind of broken. Let's see if this even types. Oh, it does type. Okay, what does this do? Wait, that's not possible. All right, and let's do one that's longer. Okay. It's not quite right though. So like something here. Whoops, wrong. Okay. Change this to something. That's not what we want there. We want something else there. You got to think about what that something else should be. All right. Any questions about the homework before I let you guys go? Okay, so remember, no lecture next week, but the week after. We're sort of on fortnights at the moment. Just come see me or the ITLC TAs if you need any help with homework. Otherwise, I'll see you in a fortnight. Thank you.
Sorry,
No problem.
silly question.
Sure.
But this is more from the fundamental side of things because it's been annoying my brain in the last 2 hours.
Sure.
Okay,